Welcome to the 15th lecture for Physics 4B. As we move beyond electrostatics, we introduce a circuit in this lecture. For now, we are only going to spend brief time with the circuit and move on to magnetism as quickly as we can. We do need the proper introduction to electric current here to use the concept of current when we start with the magnetism. So in this lecture, we will start by talking about electrostatic assumptions that change when we step away from the static equilibrium conditions and look at the voltages in an electric circuit. Then, we will take some time to introduce the electric current, making sure to build a good mental image of a current. We have water analogies, which I think are more helpful than other analogies people might lean towards. Then we talk about resistance and Ohm's law. And we will take some time in this lecture to talk about power dissipated in a resistor. We will return to the idea of power as we talk about circuits more later in the semester. That's it for the introductions to circuits. We do have DC circuit analysis lectures next, and depending on your approach, you can look at them immediately after this lecture, or you can return to them near the end of the semester, just before we start time-dependent circuits and AC circuits. Either way, our coverage of magnetism won't depend on techniques for DC circuit analysis. So we are actually getting to part of electricity that's most practical. So, the things that we've been talking about, electric fields, have been very abstract. If before this class you didn't have any opportunity to build the intuition for electric field, that's perfectly understandable. But by the time we started talking about voltage, that should have started sounding more familiar because you see the word voltage around in everyday life. And what we are really leading up to is this. Here is a paradox that you probably have seen before. This is a light bulb, and this is, I guess we call it power supply. But what it really is it's a voltage supply. You see volt written here. So I have these knobs that I can control to increase the voltage that I'm applying to this light bulb. And when I increase it enough, you see it there. And when I increase it enough, you see the light bulb start to light up. Like, how many, everyone here has seen the light bulb light up? So this is what we are getting to today, and we'll spend a little bit of time, about a week of time, and we are actually going to come back to circuits towards the end of the semester. So what we are covering now is something called the DC circuit, and to cover AC circuits, alternating current circuits, we need to cover more physics. So I just want to remind you what we have been talking about in static electricity. So what we've been talking about in static electricity, it particularly has to do with what we said about conductors. So for conductors, what do we know about behavior of conductors in static electricity? Like, what are some of the conductor properties you know?
Conductors, they allow spark, easily move.
So the definition of conductor is that, so you could call that definition that electrons or the charges are able to move around. So charges are able to move around, but charges can't move. But in terms of problem solving, there were at least 3 properties of conductor that we covered. 2 of them are kind of important for you to remember. So, we do start off from the fact that inside the conductors, charges can move. That's the definition. But when you're doing electrostatic problems, you kind of have to know the properties of conductor beyond the definition. You get it from the definition, but if you are trying to redrive this in an exam or a quiz, you won't have enough time and you won't be able to. So what are some of those properties that we covered that applies to conductors? Of course.
Electric field is 0.
Yeah, that inside electric field is 0. What else? There's 2 more properties, but I'm looking for actually one of the other properties that we covered in class. That outside the conductor electric field is perpendicular. That's one of the properties, but not what I'm looking for. I'm looking for the other one. Yeah, so also inside, voltage remains the same, or another way to put it is change in voltage across conductor is 0. Right? So this is what we have said about conductors so far. And I can't emphasize enough that these properties that we have talked about, it applies for static electricity. Because the way we got to these properties was that we were assuming static equilibrium. That's where we use this definition. If it's a static equilibrium, then charges inside the conductor cannot have any forces on it. That's why electric field was 0, and so on. So the reason I'm highlighting this is now we are going to move beyond this assumption. We are going to move on to situations where this assumption will fail. So if you are somehow leaning on this beyond the static electricity, you are not starting at the right place. So let me do this quick demo. So I have this long conducting wire prepared. Let me just pass around the little segments of the same wire material. I found this roll of, oh, you guys probably can see, roll of wire, just pass it around so that everyone can see what it is. Pass this and pass it to the center, please, so that people can see it. I mean, it's just a regular piece of wire. There's nothing special about these wires. I had 3 prepared, but I think I dropped one of them. Anyways, while it's going around, so it's just a regular piece of wire. I think it might be made out of steel because it rusts. I was just sandpapering off of the rust. So this is a piece of conductor. And normally what you do say is that because this is conductor, voltage difference from one end to the other end of the wire is 0, according to what we have said. And even with this power supply, you can kind of see it. Let me actually set up some of these settings for safety purposes. So I'm going to light up this light bulb. And I'm just touching the second knob to do something that I'll explain later. Wait, I might, yeah. I have to set this for safety purposes. All right. I'll explain what the second knob is doing. All right, that's good enough. All right. So what we say about conductors, it holds most of the time. So I have this power supply, these 2 wires connected to the power supply. Right now, the voltage between these 2, it reads 6 volts. That's what you are seeing on the screen over there. Thank you. Everyone got to see the wire, nothing special. Right now it says 6 volts. So what it's saying is that there's a voltage difference of 6 volts between them. Now, when I allow these conductors to touch, by the way, don't do this too often. It's, don't do this with regular battery, please. This power supply has a safety feature built in, where it is actually safe for me to do it. You do see a little bit of spark. When I do this, sometimes you see a spark. But so, when I allow these conductors to touch, then there's 0 volt between them. Well, close enough to 0, right? So this is what we have been talking about, that conductors are, that defines equipotential. But when you set up a particular arrangement, sometimes you don't see 0 volt between 2 ends of a conductor. So let me connect one of the wires to this end here. So wire connected here. Now let me wrap it around for good measure. And so right now the other end is not connected, so it's reading 6 volts as you might expect. But when I connect this at this end here, oops. Now it doesn't quite read 0 volt anymore. It's reading 0.4 volts. And in fact, how many volt it reads, it'll depend on where I place it. Let me take this length of the wire, take about half its length, and this is about half its length, and connect it here. It was 0.4 volts before, right? When I connect it here now it's 0.2 volts. Now let me do one more thing. So let me take the same length of wire, but connect it twice. So double up the wire. So connect this end to this here, and connect the other end, same length as before, here. And this time, well, it's somewhere between 0.2 and 0.1, because it's flickering between the two. So you get, so how much voltage that I'm reading at that other end, it depends on the exact arrangement of this wire. So this is the type of situation that now we'll start to deal with that does not, where the assumption of static equilibrium doesn't hold anymore. So let's try to describe exactly in what way it's not a static equilibrium anymore and what that means. So let me call this intro to circuit. So let me draw a picture of this conducting wire, because this wire is so thin, let me draw it a little bit bigger. So imagine this sort of cylinder is a representation of the conducting wire. So what we do by connecting these leads from the power supply to the conducting wire is that we are applying a voltage across this conductor. We apply a voltage at this end, called, let's say, voltage of 0 volts. Sorry, I'm using V in too many ways. Well, I'll use this stylized V when I'm in volts. And let's say at this end, I'm applying voltage of, let's just say 10 volts, just so that we have some specific number to talk about. So if this wasn't a conducting path, if there wasn't this conducting path between them, what would this mean? Having 0 volt here and 10 volt here. Like, imagine that instead of this being a conductor, imagine this was like the capacitor setup, where I have a plate on the left that's charged to 0 volt, and plate on the right that's also charged to 10 volts. Like, if there wasn't conducting path, what would putting this voltage difference mean? There's electric field between these two. How was that electric field set up? In fact, let me draw the electric. What direction would the electric field go? To the, let's see, to the left, right? Yeah, okay. Yeah. From high voltage to low voltage. So it would mean there's some kind of electric field between them. And why is there electric field between them? I mean, you could say it's because there's voltage difference, but so there's a third feature that having this voltage difference involves.
Charge separation?
Yeah, there's a charge. On this positive plate, there should be some positive charges here. And on this negative plate, there should be some negative charges here. And so that's the electrostatic picture. When we are now dealing with a circuit where it might not be at static equilibrium anymore, what we are saying is, all right, instead of these two being separated, now they are connected by a conducting material. And I want to look at what should change now that these two ends are connected by a conductor. So this is where you have to have some constraints given to you. So, in static electricity, essentially what we said was, if we are dealing with static electricity, what we would say is that this voltage is not a known quantity. Now, initially there might have been 0 and 10 volts. Initially there might have been negative and positive charge separation. But in static electricity, what we say is, well, after this initial setup, we are going to remove our hands, let whatever happens happen, and then look at it again when everything's have come to static equilibrium. In other words, we are saying we are not going to apply voltage anymore. Let's see what happens. What would happen is negative charge and positive charge will attract each other. It'll be on net, neutral all the way throughout, be at 0 volt, have 0 electric field. Like that would be the situation, right? So that's what we did in static, whenever we are dealing with a static equilibrium. Now we are changing the terms. Now we are saying that, no, we are going to continue to apply 0 volts and 10 volts at these two ends. And that's kinda what we are doing with this. In other words, let me change the numbers so that it actually, what I'm saying in words matches physically what I can make happen. So let's say with this, I'm trying to apply 0.5 volts. And let me fiddle with the second knob a little bit. And what we are saying is that, so now there will be situations where if I'm trying to apply 0.5 volts, I can't. Physically, I'm just not able to apply 0.5 volts. But in circuits, what we want to deal with now is deal with the situations where the power supply is trying to supply 0.5 volts, and the rest of the setup is set up in such a way that the power supply is able to. Move this. Power supply is able to. So I'm trying to apply 0.5 volts between these two ends of the wire, and I can. So that's the situation. So that's the change in condition that we are now doing. So before, what we said was, it's the static equilibrium condition. This is what we are holding true, that charges don't move. When we get to circuits, now we are getting rid of that, and we are holding something else constant. And depending on the problem, this will change. But for this initial discussion, let's say we are holding change in voltage, difference in voltage constant. So what else, if we are holding this constant, what changes? Or actually better, what doesn't change? When you look at it here, based on saying that the voltage difference is constant, can you say if there's something here that should not change? As in, so the charges and the electric field, we drew them based on electrostatic picture. So let's just go through them one by one. The electric field, should it remain the same, or should it somehow change? So if your intuition says that electric field in here should be 0, I want you to think through it carefully. Yeah, so we are not saying that it's a static equilibrium anymore. So I don't want you to go to this anymore, because deriving these two properties, it depended on assuming static equilibrium. We are saying, I don't know what's happening to static equilibrium. So if your intuition says that electric field should be 0 in here, what I want you to do is I want you to fall back on the definitions. So this is the definition that relates the voltage difference to the electric field. This was the definition of voltage. The reason we call this definition is because it never fails. It's always true. So voltage difference from A to B is defined as this integral from A to B of the electric field dot product with dl. The picture that I'm sketching here, having a non-zero voltage difference from one end to the other end. Here, having a non-end voltage difference from one end of the conductor to the other end of the conductor. There's 0.5 volts right there. Is that consistent with having 0 electric field inside the conductor? Yeah, it's not. So here, now we have to say, because there's a voltage difference, there is actually electric field inside the conductor. So that's one of the things that change, or actually doesn't change from static situation. So this electric field that we said should be there in the static equilibrium situation based on the fact that there's a voltage difference here. That electric field remains. So it's still there. So here, what we are doing is we are doing what we needed to do to maintain this voltage difference. So if we have the same voltage separation, voltage difference, and we have this electric field, that must mean that we still have this charge separation. Because without this charge separation, then how will we have electric field? To have non-zero electric field, I must have some charge accumulation somewhere, right? Now, what happens with these charges? Like, imagine what happens in the next moment. Do these charges just remain where they are, or do something? Let's say the positive charges, they don't move. They are protons or whatever. What happens with these negative charges in the next moment? They move, right? So these negative charges, they will feel force from this electric field. So they will actually start to move this way. Negative charges will start to move to the right here, right? In other words, you are losing negative charges here. And that also means you are actually losing positive charges here also. Because when negative charges finally reach this end, then by that same amount, this end is that much, it has less net charge there. Okay? So so there must be something that we are doing to continue to maintain this voltage difference and continue to maintain this electric field as we are losing these charges. Guesses? There's a supply of charges that's coming in. That's really what this power supply is doing. So if I was measuring voltage difference at this end with another voltmeter, then the moment I turn off the power supply, the voltage difference will go to 0. The moment the power supply doesn't supply charges anymore, it'll go to 0. So to maintain this setup, there must be a continuous supply of negative charges that are coming in to replace the charges that are being lost as they move from one end to the other. And here, there must be continuous sort of extraction of these negative charges from this end, so that as negative charges come in, they don't make this end net charge 0, that this end remains net charge positive. So there has to be a continuous flow of this charge here. And this flow of charge here is what we refer to as current, or electric current. And so this is now what we need to explicitly deal with. You can look at it this way. When we said in static electricity, assuming static equilibrium, another way to say the same thing is to say the current movement of charge is equal to 0. That's what we were assuming before. And now, as we get to circuits, we are going to say my current, it might not be 0. In fact, it's definitely not 0 in a situation like this. So I probably should define current. And I want to define current in a careful way, because this is something that you will see a lot. And depending on what reference material you're looking at, you might even see something like this. I is equal to dq dt. And I try to never write this down without there being some sort of explanation. Because I think it's important for you to know exactly what we are measuring here. So with the current, we are trying to measure a flow rate of how quickly the charges are flowing. How do you think we should measure it? What's some, I don't know, reasonable, let me put it this way. In what unit should we measure current?
Something similar to voltage.
Well, it might relate to voltage, but we will eventually relate it to voltage, but not right now. Right now, all that voltage is doing is that it's just maintaining this. So there being this voltage difference, it's just saying that something is being done from outside to maintain this charge separation by continuous flow of the charges. So this is what I'm imagining. Imagine you are imagine you are a little observer standing here, looking at all these charges flowing. And the other ends are so far away that you are not going to be able to see it. You don't really see any voltage difference. I want you to describe, okay, as an observer standing here, what can I measure to see what my current is? Or let me put it this way. So the most useful analogy to build up your intuition about electrical current is when you say the word current, what else do we call current? Can you tell me other words that are not electrical current, but would be used with a noun current, not the adjective current? Right, river current. So this word reminds you of river current or ocean current or whatever. In that context, what does the word current refer to? Flow of water, right? So that's what I want you to imagine here. So here I was drawing the picture of electrical things, but if you imagine this as just a water pipe, and there's water flowing through it, then that would give you a useful analogy to electrical current. So I want you to think of measuring this electrical current as, well, we want to measure it the exact same way we would measure water current. So if you have water current, in what units do you think you would measure water current in? Okay, so there are different ways of measuring water current. So imagine you have a pipe here. So I think what Kevin was trying to say was you were describing the water velocity. As in, imagine this is filled up with water. Then if you are tracking a little section of this water here, you can imagine dropping a little bit of ink droplet and see how fast it's moving. And you are trying to measure some flow speed. But that doesn't actually tell you how much water is flowing, because this rate can be really high, but the water pipe can be so narrow so that not much amount of water is flowing. So when I talk about the word flow rate, really what I'm interested in is with the total amount of water that's flowing. So in what units would you measure the total amount of water that's flowing?
Gallons per hour.
Something like gallons, some unit of amount per time, right? So flow rate, so it would be, denominator would be second, and the numerator will be something that indicates how much amount. It can be volume, like gallons, or if you're trying to keep to SI unit, it might be kilograms if you're doing it by mass, or if you're doing it by volume, it might be cubic meter. So that's how we measure flow rate with any fluid. And I want you to separate this flow rate from the flow speed. It's two different things. And it's the same thing with the current here. So with the current, mainly what we are interested in is the flow rate. So how much charge is flowing in a given amount of time. So the unit that you should measure current in it's going to be in coulombs. Amount of charge, unit of charge, right? It's going to be measured in coulombs per second. So how are we counting the amount of charges? So this is the unit it's going to be in. But let me actually describe how this guy would actually measure current. So, Miguel, when you said you measure flow rate in gallons per hour, how do you measure the gallons per hour?
You measure how much water travels from one location to another location throughout that period of time.
Okay, one location to another location. So this is a picture I can kind of imagine doing. Here's a water reservoir here that you are drawing water out of. And here's the water reservoir at this other end that you are putting water into. And what you are saying is, you look at, all right, how much water this has lost, and how much water this has gained, and it would be the same amount. And if you are saying that your flow rate was 1 gallon per hour, then which is very slow, then in 1 hour, you would have seen this rise by amount of 1 gallon, right? That's what you're saying, right? Now, I want to change the description of this in a way that I have a local description. As in, so here, I had to look at the entire picture globally. As in, I had to look at how much was lost here, how much was gained here. I mean, they're going to be the same. But I had to kind of look at the entire system. I want to come up with a way of measuring this so that I can actually look at a single point. The way your meters are set up, both the water meters and the electricity meter in your house, it's set up at a single point. Like a meter doesn't have access to anything else in the house except a single point it is. So I want to describe how we measure flow rate. If all we have access to is, let's say, a single point here. So at this single, well, I say point, but this single cross section, let's say that's all I have access to. How would I measure flow rate? Oh, we're going to say something, Chris?
Would it be like velocity by the cross-section of the pipe or something?
So I could measure velocity, and actually we'll get to that description in a bit. But I want to describe it before describing any fluid velocity. So I kind of want to ignore this fluid velocity description for now.
Do you know how many particles would pass that given line during a period of time?
Yeah. So it's a really simple measurement. It's a simple measurement. How much? So this is the picture I want you to imagine. Some amount of water, which is all flowing at some speed. Now some of them will cross. Let's say all these represent movement of water in 1 second. Some of these cross, some of them don't. But as someone, I guess you could think of this like a toll gate. As the toll gate keeper, he can measure how many of the water crosses, how much doesn't. Amount of water that crosses this point is what gets counted into this 1 gallon. Amount of water that doesn't, either because it's already on this side or because it's too far away on this side, then that wouldn't get counted. So when we talk about electrical current, it is the qualitative description of that is number of charges per time. But I want you to be careful what we mean by number of charges. And the number of charges is, imagine that this guy is setting up a toll gate here, sort of a single plane that goes through this material and has the cross-sectional area. And what this guy is counting is in 1 second, how many charges are crossing over from one side to the other side. That's all he's looking at. So when we say number of charges, it's the number of charges that, let me call it cross checkpoint. That makes intuitive sense? All right. So that's in this expression here, that's what's meant by delta Q. How many charges are crossing the checkpoint. Now, if we change this, let me give you 2 hypotheticals to see if this description makes sense. If we change the amount of time that we are measuring the charges for, how many of them will cross, will it change this ratio fraction? Now, so let's say, let's just make the numbers concrete. In this picture, let's say over a time of, let's say that over a time of 1 second, you measured 1 coulomb of charges crossing across this boundary. So you are measuring current of right now 1 coulomb per second. There's actually a unit for this coulomb per second. That unit is, in that SI unit for coulomb per second, you can describe this as 1 ampere. Ampere is the unit of current that we will deal with soon. And that's actually, well, that's why this says AMP. It's for ampere. So the second gauge here is actually measuring current. And the second knob is setting the maximum amount of current that can flow. So, let's say to measure 1 ampere, you did it by measuring for 1 second, and in that 1 second, this guy measured 1 coulomb of charge crossing across this boundary. Now, imagine you change how long you measure this for. Instead of 1 second, you measure it for 2 seconds. Will you now suddenly measure 0.5 ampere if you didn't change anything else here? Yeah, I want you to be careful here. So imagine what happens in the next second that you didn't see before. So I want you to imagine a kind of a steady state situation. So it's not steady state in the sense that it's a static equilibrium. It's not. We got rid of that. But it's in some sense steady state. So it's with respect to that steady state, we call this DC circuit. So we call this a DC circuit, which makes more, the phrase of DC makes more sense once you introduce AC, alternating current. But the situation that we are looking at right now, it's still in some kind of sense static. I mean, so charges are moving around. So not in that kind of sense it's static, but the rate at which charges are moving is the same. Imagine that you have a water pipe which has a constant flow rate. So it has a constant flow rate of 1 gallon per hour. So how many gallons of water cross this point if you wait for 2 hours? 2 gallons, right? So does the flow rate depend on whether you measure for 1 hour or 2 hours? Miguel? Right? It's the basic idea of how we define the rate. And if we say that the rate is constant, then it doesn't matter if you measure for 10 hours. So coming back to this picture, we are going to set up the situation here so that the current is constant. So if you measure for 2 seconds, how many coulombs do you expect to measure? Miguel? 2 coulombs. Yeah, 2 coulombs. So when you change time, what will change is not the current. We are going to set up the situation so that what will change is the number of charges. And this is how you can imagine it. Imagine that, so I drew only 3 charges here, but let me draw 3 more so that I can express a little bit better what I mean. Let's say they all are moving at the same speed. So this is how you can imagine it. In 1 second, the number of charges that will cross this boundary can be expressed by this. It can be expressed by a number of charges that fall within this volume here. Let's say, so if we imagine some kind of speed, then charges that are here have enough speed to cross the boundary in 1 second. When you decide to measure for 2 seconds, the number of the volume that contains the charges that will cross the boundary, it changes. If you wait for twice as long of a time, then the distance that, given the same speed, distance that can be covered in that twice as long a time now changes. So that there's now double the amount of charge that can cross that boundary in the given time of 2 seconds. Right? So that's current. It's defined as number of charges that cross a particular checkpoint in a given amount of time, and that what that given amount of time doesn't actually matter. If you measure it for 0.1 second, then if this is 0.1 second instead of 2, then there will be 0.1 coulombs that cross the boundary because this will be so much narrower. There will be fewer charges that can cross. Okay? So that's one way where you can imagine changing something that doesn't actually change anything. Then you change time, that doesn't actually change anything. I want you to think about the second thing that we might consider, once again, changing, and see if anything real changes. So this is observer A that was measuring current at this point. Let's say someone else sets up an observation point at some point later. So I have an observer B who set up another checkpoint here and measures current here. How do you think current at point A? So the symbol we use for current, by the way, is I. That's why it's I here. I don't know why it's I. It's just I. Let's say current at point A is IA, and current at point B is IB. From knowing current at point A, do you know anything about current at point B? Katie, what do you say? How are these two related? That they should be the same. Yeah, they should be the same. If you don't have that intuition, I want you to fall back to this model here. So let's say you can measure current flow rate of the water here at two different points. You could measure it here. See how much water is entering. Let me call that flow rate in. Or you can measure it here. How much water is leaving the volume, flow rate out. So hopefully more of you have intuition that this flow rate in and out should equal. But why are they equal? Like, why couldn't there be more water entering in here than leaving?
There'd be like a bunch of water accumulating in the middle.
Yeah, that would mean because mass is conserved. If more water flows in than out, that means the water is accumulating in the middle. And one of the properties of liquid is that they are really hard to compress. So to a very good approximation, amount of volume coming in should equal amount of volume going out. Because it's so hard to compress them that whatever comes in has to mean something gets pushed out by the same amount. And it's the exact same thing with the current, exact same thing with the charges. However many charges are coming in at one end, it turns out charges are super hard to compress. As in, if you try to accumulate even tiniest amount of coulombs of charge in a wire like this, it involves such a huge amount of voltage and force that you just can't do it. So the very good approximation to make is that there's no significant charge accumulation anywhere here. So what that means is however much charges are coming in here, exact same amount of charge has to go out here. So this is another useful thing to know about current. Even though we define it with reference to a particular checkpoint, where the checkpoint is actually doesn't matter. As long as you haven't broken off a branch so that charges can go elsewhere, checkpoint can be along anywhere along a single branch of conductor. Okay? So what I want you to spend the remaining time to talk about is some of the conceptual barriers in thinking through the answer here. I think it starts from, how do I put it? It's not necessarily useful. So I don't want to say it's useful. I think it's attractive on the face of it to think of current like cars moving along a freeway. And when you think of current that way, there is something very unintuitive about the answers to A and B and how this is shaped here. So what I'm telling you here is that on the broadest part of the conductor, where if I'm taking resistance per length, the resistance per length here might be the smallest. And I'm telling you that amount of current that crosses through this cross section at any point in time is the exact same amount of current as through the cross section here. And if you've gone the route of thinking of charges moving like cars moving on a road, then using that wrong analogy to ground your intuition, you would wrongly go into thinking that in this wider part, current flows more easily, so more current flows. And in this narrower part, current flows less easily, so current is less there. That's an easy, intuitive, conceptual mistake to make. And what I want to highlight here is that one, that's wrong. That's just not how it works at all. And what I want to offer you instead is, instead of car analogy, which happens to fail here unless you take a super careful care to set it up correctly. And I think all of that ends up being too much work. I want to give you more more useful analogy that matches up much more closely to current flow. And that's what you did for the opening discussion this week, the water analogy. So I want to show you a simulation involving water flow and show you how that water analogy can help address anything that you see here that seems unintuitive. Now, so let me go to the simulation. A brief kind of explanation of why. Well, I mean, water analogy is useful, but I think I initially actually wanted to find the actual electricity simulation, and none of these simulations do what I wanted to do. So that's why I just have to go to the water analogy, because they do have a pretty good fluid dynamics simulation that does exactly what I wanted to do. It's this one called the fluid pressure and flow. I think if you're in my physics 4A, you might have seen one of the lecture videos where I do use this to, I don't know, illustrate Bernoulli's principle, which technically in my physics 4A isn't a required topic, it's optional topic. So, for a bunch of different reasons, this is a good thing to revisit, see what intuition we can get out of this physical picture. And so let me go through that in the next 4 or 5 minutes. By the way, this is an interesting innovation at FED. Java simulations, it used to be that you had to download, but I think these days you can just run it right in your browser. So, I mean, I don't think it might not run on every device, but at least this is a really interesting innovation. So I think it's this simulation that I had mostly in mind, although you can definitely, like with the water tower, there's a kind of lessons you can draw from here in terms of how pressure or the height difference matches the voltage. But it's the flow one that I want to talk about the most. All right, so this is the fluid flow simulation, and let's see. I guess I should tell you the elements of the analogy. So I think the physical objects are fairly obvious what they represent. These that represent, representative samples of water element, and it would represent the exact same thing in the electrical context, like a charge elements. So that's what those dots represent. So this is a visual way to represent a flow, whether it's a charge flow or water flow. And there's a way where you can measure speed, and so here the speed that they're measuring is would match up with what your textbook calls a drift velocity. I think if you're looking at your textbook, there's a place somewhere here. I think it's in this section. Drift velocity, yeah. So The reason this term is introduced is because, electrons, microscopic objects, their thermal velocity is actually much higher than drift velocity. So drift velocity is kind of an average velocity moving in one direction, and that's what this speed would represent. So I think that's a kind of one-to-one thing. The place where you have to kind of match with the language of the fluid flow with electrical current flow is the ones dealing with the pressure. So I think in the fluid dynamics context, there are two different things that kind of match up with the pressure. There's a kind of something that would represent the potential energy. Like if one end of the pipe is higher than the other end, then there's a potential energy difference between here and here. And I think in the case of this simulation, the potential energy difference actually does lead to, so trying to get the bottom of each pipe, it does lead to actual pressure difference. So, so yeah, there's that. And that pressure difference actually does drive the, the way this simulation is set up, I don't think it actually, because it's set up to set a constant flow rate, it wouldn't actually set up, cause the fluid to flow any faster. So never mind that. But in the fluid context, I think maybe more succinct way to say this, it's the pressure difference that drives the flow of materials like this, and the electrical version, electrical analog to the pressure or pressure difference is the voltage or the voltage difference. Now, with this simulation, there is no pressure difference between one end of the pipe to the other end of the pipe. And, that is actually a real situation you can have if you have a frictionless material, if you have resistance-less material. If you have a superconductor, you actually don't need any voltage difference between the ends of the superconductor to have a persistent current setup. So there's a real thing. In this simulation, for some reason, turning on the friction does nothing. So I don't know. So let's not talk about that too much. What I do want to talk about is how to connect to your intuition about this kind of flow and how different aspects of this change what different aspects change and what don't change as you change different parameters here. So the main parameter you can change here is the width of the pipe, and that's yeah, width of the pipe. You can change it there, here, and that change in the width of the pipe is what would correspond to change in the width of this conductor. And you can see in the simulation already how this narrowed pipe affects the flow of the material. And I guess I hope that this makes intuitive sense, that when this stuff flows through this narrower portion, the water flow doesn't slow down as it flows through the narrow portion. It actually speeds up. And the reason it has to speed up has to do with what the actual constraint in the flow of material here is. The constraint here is the flow rate. It's volumes per second. That's the actual constraint here. So when I have flux meter, as I move this flux meter around, it's been So this simulation has set up so that flow rate is fixed here. And I can describe that as flow rate being fixed at the entrance end. Then by the property of the water, this flow rate has to be the flow rate through any particular cross section throughout this entire length. And the property of water that's most relevant here is that it's incompressible. That so I specify the flow rate in volume per second, and whatever volume of water that comes in, that's the same volume that has to leave here every second. It's this is the general property of liquid that they don't compress that well. So however much flow is coming in, that pushes out the flow all the way down the chain, all the way out here. So that's the real constraint here. And if you think through the traffic example, that's not really the constraint that you have under most traffic circumstances, because the traffic fluid is compressible. You can have distances between cars that change quite fluidly. So, so the thing to be mindful here is that it's the flow rate that's kept constant. And in order to keep the flow rate the same as the cross-sectional area changes, what changes is, you know what, I have no idea how they define flux. Oh, I guess the flux is the flow rate per area. So I think rather than flux, what I think is more useful as a kind of physical thing is the speed of the particles. So in order to have the same flow rate here as here, particles simply have to move faster. That is the speed, the drift speed of velocity v times the cross-sectional area has to be constant. So that as the cross-sectional area decreases, speed has to increase. Then you might still wonder that, like, how does that come to be? Because, I mean, it, it feels like there has to be some other things changing as the particles move faster here. And especially if you think in microscopic terms, that's definitely correct, because the particles moving through here have more kinetic energy. They are moving faster in terms of drift velocity. And when you measure the pressure at different points, you see why. So this is entirely about fluids. So this fluid flowing kind of from midpoint to here, there's a distinct pressure difference. So it's this pressure difference that pushes the water element through, so that it's faster here. And once it's through this portion, then the pressure difference is the other way, and that serves to slow them down. And you can see a similar situation with the electrical current flow here and voltage here. So I said, referring to why the correct answer here might be unintuitive, that when you are looking at resistance per length, that resistance per length would be less here compared to here, but still the amount of electric current flow is the same. Well, if you look at the voltage change per length, what you will find that voltage change here is less per length compared to the voltage change here per length. So that when you say apply Ohm's law over that slice of the conductor, that that the current ends up being the same, because the resistance of this slice is the lower, but voltage difference across the slice is also lower compared to the resistance here and the voltage difference across that slice. And that intuition will help you as you work and think through, let's say, series circuit. Because when you have series circuit, one of the things that you have to get through early on is that the current through the entire series circuit is constant. The current through a low resistance element in a series circuit and the current through the high resistance element in a series circuit, they're the same. And the reasoning that you apply there is the exact same reasoning that applies to this one. That's why the correct conceptual understanding of this setup is useful, even as you are moving into more detailed circuit analysis. Because then when you encounter that situation with the series resistors, you don't see that as something unusual. It's something that was to be expected. So that's what I want you to talk through, and the simulation I want you to show. But let's say we defined all the current, we defined it as some amount of charge flowing through past a point in some amount of time. And now what we want to do is, so as you saw in the demonstration, the way we got current to flow is by applying a voltage across a conductor. So I want to describe the experimental law that tells you how that happens. So this is the law called Ohm's law. And at least until I get tired of it, I'm going to put quotation marks around the law. Because Ohm's law is an exception to the fact that most of the actual laws you see in this class, they are fundamental laws. There are no exceptions. There's no exception to Gauss's law. If you ever see me say in a multiple choice question, say that this is a rare exception to Gauss's law, well, that's a false choice. Ohm's law is an exception in the sense it's not really a law. It's more of something that happens commonly. So let me demonstrate to you the situation where it happens commonly and see what the law says. So I'm going to turn this back on. And for safety's sake, what I'm going to do is I'm going to turn the voltage way down to 0. And this current control knob, I'm going to turn it up so that this power supply is not going to try to limit the current. I still have these two ends connected. So there's a current flowing through this conductor here as soon as I start applying voltage. So let's see what happens as I apply voltage. So I apply a little bit of voltage here. Let's see. When I apply about 0.5 volts of voltage, difference from one end to the other, then I get current of 0.22 ampere. Let's keep going. Let's try doubling the voltage from 0.4 volts to, where do I look at? 0.8 volts, 0.37. I think I can probably go as high as 1.5. So let me, so that it's easier to see, let me go from 0.5. So at 0.5 volts, it was 0.22. Let's go to 1 volt. At 1 volt, it's 0.44. And let's go all the way to 1.5 volts, 0.66. What do you think the relationship between voltage and current is? Proportional, right? Yeah, that's what Ohm discovered, that this law holds with most conductors. Now, the reason I keep putting quotation marks around the law is that it's not universal. There will be materials that don't obey this law. But so to draw that distinction, we say for ohmic materials, as in materials that obey Ohm's law. It's sort of, self-explanatory, right? And what ohmic material, it includes a lot of different things. It includes most conductors. And in fact, it might include all the conductors, because the things that don't obey this are like semiconductors. And sometimes when the conductor's temperature changes a lot, then it can be considered non-ohmic in the sense that the relationship isn't strictly linear. But so for materials that obey Ohm's law, essentially most conductors, this relationship holds. The voltage you apply is proportional to the current that you get. So we want to go a little bit past this proportional relationship. So what do you do when you want to go beyond simply saying one quantity is proportional to another quantity? Like at the very beginning of electricity, we wanted to go beyond simply saying that, so we could have said that electric force is proportional to charge, a product of charges divided by distance squared. But we want it to go beyond this. We want to say it's equal. What did we do to make this relationship equal instead of just merely proportional? Yeah, we introduced a constant here when we are dealing with electrostatics so that we can say this is equal to this. And we'll determine the constant later. So we are going to do the same thing here. With the Ohm's law, what we really want to say is we want to say that voltage is equal to some quantity involving current. So the constant of proportionality, this is what we are going to call resistance. So this is a new constant that we are introducing. It's what we call resistance. And it's a property of the object that you are dealing with. Not property of material, property of the object. I will demonstrate what I mean by that. But this is probably a good point to pause a little bit and talk about the units. So the unit of voltage is in volts, right? We've talked about that at length the other day. Unit of current, we just introduced it today. Unit of current or coulombs per second, that's in amperes. That's the new unit of current that you just heard today. So resistance also gets its own unit. There's a name for it. So unit of resistance, it's called ohm. That's the name of the unit because it comes from Ohm's law. And the symbol that you are going to see for ohm is not O or capital O. It's actually capital omega. I don't know why. I don't think we are using capital O for anything, but I guess it's too confusing with the zero. So capital omega is what we use for abbreviation of ohm. Now, what do you think 1 ohm is in terms of these other units you have seen? Like, what is 1 ohm in terms of ampere and volt?
Volts per second per charge, volts per second divided by Coulomb.
Okay, volts per. So why do you put volts on the numerator?
I was dividing it by current.
Oh, I see. You are imagining solving this for R. You can do it that way. So if you are solving Ohm's law for R, take it as a, defining the resistance R, then you would say R is equal to V divided by I. So the unit of ohm would be unit of voltage, volt, divided by unit of current, ampere. So you could say that 1 ohm is equal to volts per ampere. And as I said the other day, the units for electricity kind of can get complicated in the sense that there are a lot of interlocking relationships. So I would just stop here. And if you want to express it into coulombs and other basic quantities, then you can, but I won't. You can convert volts to joules and whatnot, and you can do that. I won't. So this is the definition of resistance. This Ohm's law relationship is how we define resistance of anything. But I want you to notice something here. So resistance of this entire wire is some amount. In fact, I think we can actually measure it. So let me put this at some reasonable value here. Let's say, let me put it at, let's see, where is it? I don't know if I can get as high as 1 amp and not anything bad happen. Let's just try that. All right, that's good. If it gets hot, I just won't touch it. Yeah. If you start to see anything burning or glowing, tell me. All right, close enough. So this piece of wire, you can say that it has resistance of, we are just measuring that there, right? So volts per current. So the resistance of that wire that you see is equal to 2.3 volts per ampere or 2.3 ohm. It's actually a pretty small resistance. Which makes sense. It's just a piece of wire. Now, what I am going to do is, let me turn this off first. I don't want to hurt myself. Is it hot? All right. Voltage-wise, it's actually pretty safe. What I'm worried about is that this might have heated up, and I don't want to burn myself. So now what I'm going to do, it's still the same piece of wire, but I'm going to change my arrangement a little bit. Instead of using the entire length of wire, I'm going to use half as much length of the wire here. What do you think will have happened to the resistance?
It would double.
Resistance would double or half?
All half, yeah.
Yeah. So, you have some sense of what this R means here, right? The name says resistance. It resists current. And you can actually, the higher the R is, the more voltage you will need to put through the same current. So this R does measure resistance to current. The higher the R is, the lower the current you have if your voltage is the same. So here, before I got 1 ampere to flow with 2.3 volts applied. I'm still going to be applying the same amount of voltage. Let's see how much current flows now, assuming I don't break anything. Did I break anything? All right, yeah, I'm starting to break something. So 2.3 volts, it's not quite double. So it's probably easier to see this if I, oh, it's actually going to be hard. As I keep saying, this is a pretty low resistance. So what the resistance of half wire, what it's supposed to be is half of this, approximately 1.2 ohm, which means, let me actually do it this way. So having turned it on, let me reduce the voltage until the current goes down to 1. So right now I see 1.4 instead of 1.2. And that small difference is actually amount of resistance in this wire. Because, as I keep saying, this is only a piece of wire. It's not some specially made resistor. So I made the length of this thing half, but what you have to keep in mind is that I have these other wires here. So there's something like maybe 0.2, 0.5 ohm of resistance in the rest of the system. But you kind of see here that when I made the length half, the resistance went down to about a half. So when you are looking at the resistance, the quantity that we measure in ohm, it's the property of the object. It's a property of object. So in terms of hearing that this wire has resistance of 2 ohm is as useful as you hearing that this mass has mass of 500 grams. Good, if you want to use this to do something. But if you want to record this in a table for other engineers to look up, that's not useful at all. Like, why do I care that this object has mass of 0.5 kilograms? Why do I care that this piece of wire has resistance of 2 ohm? Like, I don't care all that much. So in order to describe property of material, this is made out of steel or iron. You want to know the property of the iron. And there the idea we use is an idea called, the term that we use to refer to this idea is the phrase resistivity. And what I want to get at right now is the relationship between resistivity and resistance. So what's the symbol for? A symbol for resistivity is rho. Right, that makes a lot more sense. So once again, don't confuse this with the charge density rho. It's just a symbol for resistivity. So what I want to get at is some relationship between resistance R and resistivity rho. So you guys already got at a part of it. So this is the same material. Let's say we keep its material property constant. Then what you said was that the relationship, this is as far as we got. So resistivity and resistance, they should be proportional in the sense that all else being the same, if the resistivity of the material is higher, maybe I use something that has higher resistivity than iron, then the resistance would go up. And what you guys got at intuitively was that resistance is also proportional to the length of the material, right? Because intuitively, your intuition says that if I have a longer material, then there's more like things resisting flow of charges. Should that be it, or are there other things that resistivity might depend on? Yeah, cross-sectional area. So let me do it this way. I'm going to double up the cross-sectional area by doubling up the wire. So let's connect it and see what the resistance of this, the doubled up half-length wire is. So what we said before was it should be about 1.2 ohm. The actual measured value was 1.4 ohm. At some point, it's going to be harder and harder to measure because I'm going to get too close at the rest of the system. So, but let's just try it and see what we get. Turn it on. Let me, did I break anything? Okay, not yet. All right, so, understanding the huge errors involved in measuring here, my resistivity, so how do I call it? Let me call this resistance of half wire doubled up. Is about 0.8 ohm. Or, if you imagine the number I was telling you before, that the resistance in the rest of the system is like 0.4 ohm, then from this, using the same length, it went down about by half of what it was. So yeah, it's inversely proportional to the area. The larger the cross-sectional area, the smaller the resistance. So this is the relationship between resistance and resistivity. That this is the resistance and this is the resistivity. It's a simple relationship, as in you guys could guess it almost intuitively. And this, this will be useful for some of the homework questions, because the homework question will give you some material that you're looking at and ask you what is the what is the resistance of the material if you know these geometric parameters. Okay. Questions, comments? So this is a pretty simple law, and we are actually going to be using it a lot. For what I'm calling simple law, we are actually going to be using Ohm's law a lot. This is one of the most important laws when you're dealing with the circuit. It's because whenever you know voltage or current of the circuit, and resistance is usually given as some constant, then it lets you figure out the other thing. I think I said at the beginning of the semester that you are going to see a lot of relationships that relate three quantities together, like ideal gas law did. This is one of those. It relates voltage, resistance, and current together, and you're going to use this a lot, the way you used the ideal gas a lot, whenever you're dealing with the circuits. Yeah. I think I have enough time to actually talk about the microscopic view of how current is flowing. Let me write it down here. Microscopic view of current flow. So what I want you to imagine is, let's say you have this pipe which represents a piece of wire or some conductor. And you set up a checkpoint like the one that we are describing here. And at this checkpoint, you measure some amount of current flowing. Okay? Then, now what I'm trying to get at is, I want to actually consider the movement of individual charges. So let's say I have current flowing from left to right, some amount I, and I want to describe this in terms of actual makeup of this material. So what I want you to imagine is that within this conductor are free charges, each of some charge plus Q. Okay? And which are, moving at some speed, which are moving at some speed to the right. Let me call this some kind of average speed. So, like with the kinetic theory of gas, when you have such a large collection of particles, they're going to have their individual velocities. But I'll just say, all right, some average velocity moving to right. We actually have a word for this. This is called drift velocity. Because if I wasn't applying any voltage, they would have, on average, 0 velocity. But once I apply a voltage difference, then they will have some non-zero drift velocity. Yeah? So what else do you think you need to know to figure out what the amount of current is? So remember, the current is measured in units of coulombs per second. Right? What you have so far are two quantities. You know, unit of one quantity here, that's given in coulombs. But unit of this other quantity, it's a little bit weird. I mean, you do have a sense that drift velocity will be involved in description of current, right? But the velocity, like all velocities, it's given in units of meters per second. So you got this length, unit of length here that you kind of don't want in the end. You want to get rid of it. So how do we get rid of it? Divided by what? I don't have any quantity of length here. Yeah, it's hard to guess when you see it for the first time. So let me draw a picture of what you're considering here. Actually, what you're considering here is the exact same things that I was describing earlier. So I'm trying to measure current. So what I'm trying to do is, all right, I look at how many particles are passing through in some amount of time. So I want to describe current as some number of charges divided by some amount of time, delta t, right? And let's just say we are, let's see. Let's say we look at some region. So I think this is one way I can count the number of charges that will cross the surface. So starting from here, I look back some distance, d. And this is how I'm going to pick my distance d. My distance d will be based on the amount of time that I'm going to look at and the amount of speed. So d will be, let me write it down first, the average velocity divided by, average velocity multiplied by the delta t that I'll look at. What do you think separates the charges within this distance from the charges outside that distance? What's the difference? What's the one thing you can say about the charges that lie within this volume? They are all assumed to be moving at the same average velocity. So that's true of every single charge here. But something's different about charge A here compared to charge B here. What's the dividing line? Sorry. Closer to the checkpoint. In fact, this parameter is d. When you look at this definition here, it was chosen so that whatever charges within the distance d will be able to cross the checkpoint in the time delta t. Whatever charges outside won't be able to cross it. Yeah? So if I count all the charges that are within distance d, that will be my number of charges. So let me count it this way. I'm going to need, so I feel like I have all the parameters I will need for the volume of this space. So I will need to introduce a couple more. So I will need to know the area, cross-sectional area. So cross-sectional area times d will give me the volume, right? But I don't want volume, I want number of charges. So the way I'm going to express the number of charges is this way. I'm going to say, well, number of charges, that's going to be equal to some amount of volume times charge density. And I'm just going to use a letter that's the standard letter for charge density. It's a little bit weird, lowercase n. This is what's sometimes called number density. As in, it's the number of particles per per volume. So you multiply it by volume, you get the number of particles. Oh, I forgot one. I have to multiply by charge per particle. That way I get the actual amount of charge in coulombs. Good? So does this make sense as the quantity in the numerator for the amount of charge? Yes, Miguel, does this make sense? That this expression expresses the amount of charge that's crossing this boundary in amount of time delta t. Okay, so yeah, so we write it all out. So I have delta t on the bottom. Let me write out volume in terms of d and d. So all this is n times the volume. So cross-sectional area times d times q, still divided by delta t. Let me substitute in what d is. Then this is charge density times q, amount of charge per particle, times area times d. That's drift velocity times the duration of time that we looked at. And when we write out this far, you will see the amount of time canceling out, which is what we wanted from the beginning, and like this, which matches with our intuition, that however long a time we look at shouldn't actually affect our results. So this is the microscopic description of current flow. When we are looking at some amount of current, I, that you can measure macroscopically, like using this power supply or some sort of current meter, that's going to equal some charge density times amount of charge per particle times cross-sectional area times the drift velocity of the particle. And when you work out all the units, it'll turn out that they all work out. Because from the combination of Q times V, you get coulomb times meter per second. And the combination of number density times area will actually give you 1/meter. So the unit of meter will cancel out, and you'll get this. But I want you to introduce this as a way to talk a little bit about some convention that we are going to follow. So from your knowledge of most materials, what is the actual charge that's flowing? Like what's the, so I was describing some positive charge that's moving from left to right here. Is that what actually happens in a material, or is it something different? What actually happens in a material? What's the charge that moves? It's the electrons that move. So the actual picture of charge is that when you describe a current from left to right, it's actually going to be electrons that's flowing from right to left. But we are going to use this sort of fictional convention that as if when we describe the direction of current, it's going to be as if the charge is moving or positive. So when you have negative charges flowing one way, to say that, to actually describe the direction of current, we say current is actually flowing the other way. Just the convention we have, you just have to blame Benjamin Franklin for that because he's the one responsible for us assigning a negative symbol to electrons instead of it the other way around. So that's one convention I want you to describe. The other one comes down to this, sort of the origin of Ohm's law and why Ohm's law is, quote unquote law, not the real law. So once you have this much description, then I can describe Ohm's law in the microscopic version. This is the microscopic version, or Yeah, this is the microscopic version of Ohm's law. So, Ohm's law that we stated here, it relates current to the volts, right? But as you remember, the volts are related to the electric field. So when we go microscopic, instead of describing volts, which is related to some having finite interval, we want to talk about electric field. So the microscopic version of Ohm's law tells you, well, how much electric field there is inside a conductor like this when you set up a situation for current to flow here. So microscopic version of Ohm's law says this. It says amount of electric field that you apply inside a conductor, that it's proportional to what's called current density. So let me define current density here. Current density, or the magnitude of it anyway, is amount of current divided by cross-sectional area. This makes intuitive sense as the density of current, right? That you divide it by area, not the volume. Like you don't care about the volume because along this dimension, like current, yeah. So that's why you divide by area. This is the quantity we call current density. So it's proportional. To make it equal, the way we did it for Ohm's law, we introduce quantity here, and actually it's the quantity that you have already seen, resistivity. So microscopic version of Ohm's law says that electric field is equal to the resistivity of the material times the amount of current, the current density. And this is really the reason I want you to go through this discussion, introduce all of this. We have some relationships here between some of the dynamic quantities that I want to relate. Let me tell you the two dynamic quantities I want to relate. I want to relate electric field to the drift velocity in the some sort of proportionality. Like I want to say, well, how are those two related? So I can go through this way. So electric field is equal to this. So what I can say is, well, I guess I can just take this divided by area. That will be my current density, and put it in here. So this is what I can say. Electric field, which is proportional to current density. Current density is proportional to the current itself. Holding area is constant. And current is proportional to the drift velocity. So connecting all of this together, what we are saying is that, let me flip it around. Drift velocity is proportional to electric field. And this statement should be surprising. So drift velocity is a kinematic quantity, right? It's describing speed of something. All right. What quantity does electric field relate to that can be related to kinematics of a particle? Like in the very basic definition of electric field. Force, yeah. I mean, that was the very basic definition of electric field. That electric force on a charge is given by electric field. That's how we define the electric field. So in this material, if we are saying that we have set up an electric field by application of voltage, then what we are saying is that we have set up the situation here so that each one of these particles feel a constant force to the right. Right? So do you expect velocity to be proportional to the force or Or let me put it this way. So this is the average velocity, right? Do you expect average velocity to be proportional to the force or acceleration, or somehow a little bit different? If you have some fixed distance, my intuition said that it should really be velocity squared that's proportional to the electric field. Oh, I know why. I can explain my intuition. Imagine you are pushing a particle from here to here, applying a constant force, right? Then the amount of energy that you are putting in, it can be described by amount of work you are doing, right? So on the right-hand side, let's say you describe the amount of work. That would be work. That will be force times some length that you are moving the charge across. Well, force is the electric field times the charge times the distance you are pushing the charge across. Now, the amount of work you are putting in, if you say energy is conserved, then the amount of work you are putting in should equal change in kinetic energy, right? So if that's the case, then change in the kinetic energy, let's say it's starting from rest, so it's going from rest to some final speed here. So that's 1/2 mass times final velocity squared. That should be equal to the amount of work you are putting in. So if we are going through this, then what you would have expected is that the final speed squared is proportional to the electric field. Like this is what you would have expected. But the situations that are described by Ohm's law, following from this is the result we get. It's not the speed squared that's proportional to the electric field. It's the speed that's proportional to the electric field. So how come? So which part of these steps is wrong? So I'm kind of out of time, so let me just give you the answer. The part of the step that is wrong is really here. The step that says the work that I'm doing goes into the kinetic energy of the particle. That would be true if there was no friction, if these charges didn't interact with other stuff within the material. In most cases, that's not the case. They interact. The amount of work that I'm putting in actually doesn't go into kinetic energy. It goes into the thermal energy of the particle. So the fact that this is true and this is false relates to something that we refer to by this name. And we'll talk about this when we talk about electric power, which we didn't get to today, but we will get to it sometime on Wednesday. Is the fact that this is true is related to what's called Joule heating of a material. And Joule heating refers to where you are putting in some amount of power using this power supply, and the power that you are putting, energy that you are putting in, doesn't go into increasing kinetic energy of these charges. It instead goes into increasing the thermal energy of the material wire that you are putting it through. And we describe it as Joule heating, and there's even a formula for it. I'll just write it down and we'll get to it on Wednesday. The power of Joule heating is given by amount of current squared times the resistance. And we'll get to that on Wednesday, but I want you to have this picture in your mind that whenever Ohm's law is true, once again, it's not always true, but whenever it's true, it'll always involve some kind of loss of electrical energy to frictional thermal energy. Like if you ever have a situation where that's not the case, where electrical energy is conserved, it doesn't transform into other forms of energy, then Ohm's law won't be true. Because Ohm's law being true, essentially this relationship holding true, is just contradictory with mechanical energy being conserved. Okay? I think I want to call it this way. Power dissipation in battery-resistor circuit.
This is something that I could call simplest possible circuit, in the sense that if I wanted to build some circuit that does something, so it's not a trivially simple circuit, but something that it does is reasonably simple, then I would build a circuit that looks something like this. I would need a battery to provide a voltage difference, have something interesting happening, and I need to connect that battery to what I call load. And elsewhere you hear me give a better description of load. Here, what our load will be is a resistor. So this comes at a place where we just talked about Ohm's law. So if we have some voltage that's provided by the battery, it's the voltage difference between these 2 points. So if I call this point voltage equal to 0, then the voltage at this point would be V naught. So in Ohm's law, what you have learned is that if you have some voltage that's imposed across an ohmic element or a resistor, something that you can, a circuit element that you can characterize with something called resistance, then this arrangement will result in a steady state that involves a current I. So, and this resistance is defined as the amount of voltage difference. Now, here the voltage difference that we care about is this difference here. The voltage difference from one end of the resistor to the other end of the resistor. So the resistance is defined as that voltage difference that you see divided by the current. That is this current, the same current that is going through the resistor. So this is Ohm's law. Now, with this Ohm's law in hand, we can walk through some considerations to think about how much power is dissipated in this circuit. Now, I think I need to motivate why we are talking about power. It goes back to our introduction of electric potential, like a week or two ago. Our introduction of in our introduction of electric potential, we said a lot of things. We said things like, oh, difference in voltage, it comes from this, E dot dl. In fact, that was our definition of voltage. But we also introduced the other relationships, like the relationship between change in electric potential energy and the difference in voltage. To get a relationship between change in electric potential energy and voltage, all you really need is a test charge. A test charge multiplied to voltage difference would give you a change in the potential energy of that test charge. That is what I want to focus on. This fundamental definition isn't quite as meaningful right now, so let me get rid of that. So as we look at this, how change in potential energy relates to change of voltage times the test charge, we want to relate this test charge to some other circuit element or some other circuit parameter. And as you look at this circuit, what you see is, it must relate somehow to the current. And as you relate it to the current, you remember the definition of current, that we define current as number of charges that cross checkpoint divided by some duration of time. The current is the rate at which, say, some amount of charges cross this checkpoint here. You count how many charges flow through that in how much time, take that ratio or quotient, then that'll give you the current. So to relate from current to some amount of charge, some amount of charge, what you do is, I can take the amount of current and multiply by duration of time. Then I would end up with the number of charges that crossed that checkpoint. Or I can put it this way. I'm going to abuse the notation a little bit. I'll say delta Q, meaning the amount of charges that cross that point in some time delta t. That's going to be equal to the current times the amount of time delta t. So, in this battery resistor circuit, if you are looking at what is the change in potential energy or some kind of change in energy, we can say, oh, I have this expression for amount of charge. Let me put this in for the charge here. Then we get this. The current times delta t. And you stare at this expression long enough, and you realize you can take the change in energy divided by change of time. Or to get that, you divide everything by delta t. That'll get you change in potential energy divided by change in time. That's equal to current times some change of voltage. And this portion here, this is what we associate with power. Power in physics is defined as rate of energy change. Sometimes you can relate that energy change to work being done. Sometimes you can relate to other things. In the end, it comes down to it's the rate of energy change. This is a rate of energy change. Rate at which how much did the energy of the potential energy of the battery change. And that is equal to current coming out of the battery times the voltage of the battery. Quite simple relationship, and it doesn't actually involve anything new that you need to know. It comes from everything that you already knew. It's the kind of things I love because physics is fundamental science. Now, so I think last time or in the other lecture, that's where I ended it. And I want you to add a little bit more to that. So this is the question that we can pose. Given this fundamental circuit relationship for power, for a circuit, you can say this amount of power dissipated or put in, depending on the direction, is equal to current times difference in voltage. How would the amount of power dissipated in this circuit, let me clean this up a little. So the question you could ask is, okay, so you have some circuit that's expending some amount of power given by current times the voltage of the battery. How would this power change as you so I guess this is how I want to ask the question that sometimes leads people into making a mistake. So this is how you could ask this question. How does this power depend on as a function of this resistance? Let me do it this way. So power is current times the voltage. And let's say in this particular problem, you know what your battery voltage is. That's quite common setup. You are given the battery voltage, and let's say you are given the resistance. That's also quite common. And then someone asks you, given the voltage and the resistance, what is the power as a function of that voltage and resistance? And as you are trying to answer that question, you look at this relationship here and think, okay, I know voltage. This is somehow relates to the current, but that's not useful. I want to get rid of this current. And you look at, oh, I have current here. I can solve this for current. My current is equal to delta V or V naught. Let me write it as V naught. It's going to be V naught divided by R. So I can plug that in here, and you get this relationship. The power dissipated in this circuit is equal to V naught over R, V naught times V naught, so V naught squared over R. Now, after you have worked this out, let's say someone asks you this general question. In general, do large resistors dissipate more power or less power? And if someone ever asks you that question, it's frankly a trick question, because the answer to that question ought to be, it depends. Now, you might be wondering, when you look at this expression, it doesn't look like it depends. I have power as a function of resistance. Resistance goes on the denominator. It looks like if I have a larger and larger resistance, then I should be dissipating less and less power. Is that not always true? that's the money question whenever you're dealing with math or often physics scenarios, because often we are looking for a statement that's generally true, in the sense that true always with no exceptions whatsoever. And the proposed statement, larger resistors dissipate less power, which is the statement you might come to believe looking at this expression. It's not generally true. It's true in this circumstance. I can change enough of the setting to make it so that it's not true. I can give you a counterexample, and so let me show you the counterexample. So in order to make the counterexample work, I'll have to change up this circuit a little bit. Let me change up this circuit this way. I'm going to introduce something that we call current source. So a battery is a typical example of what we call a voltage source. The job of a battery is providing a fixed voltage difference between its ends. That's what it does. Now we can replace this with a current source. Let me just spell it out. And current source is kind of what it sounds like. Its job, instead of providing providing a fixed voltage difference between the two ends, its job is to provide a fixed amount of current through the circuit, regardless of what happens. So a current source would work in such a way that if I just connected this with a wire, it would still send this amount of current. If I somehow make this resistance very, very large, it would still try to provide the same current. And now you can see that as it's trying to provide this same current, what Ohm's law will mean is that there ought to be this voltage difference between two endpoints of the resistor, so that this voltage difference is equal to the current that the current source is providing times R. So let's imagine in this scenario, how does my power dissipation depend on the parameters I control? I control the amount of current from current source, and I control the resistance. How does my power depend as a function of my current from current source and my resistance in the resistors I pick? I look at that expression again, current times voltage, and in this case, current is I naught, the current that I set at the source, and the voltage is my unknown quantity this time. And I look back at this expression where I look at, oh yeah, that's the voltage difference between the endpoints of the resistor, and because they are all connected by wire, it's the same voltage difference at the two ends of the current source. So I use this expression in place of V. When I do that, this is what you see. I naught times I naught squared times R. So as you look at this, ask and answer this question. Do you dissipate more or less power with the larger resistors? And if you try to answer based on what you had before, you're going to answer wrong. Here, resistance is just on the numerator. It's not on the denominator. So larger resistance does mean larger power. So in this setting, we would say larger resistors dissipate more power. So which is it? Does a larger resistor mean more power or less power? And And the answer, in which I'm not trying to trick anybody, is it depends. So how the amount of power dissipated depends with how resistance changes. The simple answer there is it depends. If what someone told you, the only thing that they told you is that they are changing the resistance value. I'm taking this resistor, I'm making it larger, or I'm making it smaller. With that description alone, you haven't been given enough information. You need to be able to look at additional parts of the setup to figure out more things. And as you are thinking through those different setups, you will often have three different expressions that you can consider that will be helpful. So this is the three different expressions for power. So power dissipated in a circuit, you could describe as current times voltage. That's kind of where we start from, because that we can get that easily from definitions. Now, using Ohm's law, it kind of depends on which of these two variables you choose to eliminate. If you choose to eliminate current, then you will get this, V squared over R. That's how power depends on resistance. If you choose to eliminate voltage, then you'll get this expression, I squared R. That is how power depends on resistance. And the difference between these two expressions is, so they are both true. They are they are both true at the same time. It's not as though one is true sometimes and the other true is sometimes. That's not it. It's a question of when one is more useful than the other. So if you have a situation where voltage is specified, then this is more useful for really two reasons. You are directly putting in the quantity that's specified, and also if your voltage is fixed, then as you change your resistance, you can just consider only where the resistance is in your mathematical expression. If you have a different setup where the current is fixed, then this is the more useful expression, because you can put in your fixed current and you only need to look at the how the resistance changes to get the change in the total power. But now, even in those circumstances, this expression still continues to be true. So consider the second example I gave you. If I were to use a V squared over R, this is still valid expression. It's not any less valid. The only thing you have to be careful with is as your resistance changes, your voltage will change also. So you can see from this expression, this V squared thing, it goes as I squared R squared. So, so as you increase the resistance, you're increasing your voltage also. So even though your denominator increases, your numerator increases so much faster that overall more power is dissipated. And you can do it the other way around too. Imagine we are back to where we had the battery. So you just have a battery here, and you are being asked the same question. As the resistance changes, how does the power change? And using this expression is the thing to do. That's the thing that will eliminate the chances for mistake as much as possible. But you can still use this expression. This expression is not any less valid. The only thing you have to worry about is it expressed in terms of current and resistance. And you have to remember that this current is a function of voltage. So the current, looking at this, it's gonna be V naught. So the current squared will be voltage squared divided by R squared. So here you have the situation where as resistance increases, the current decreases so much due to this R squared factor on the denominator that this combined product overall decreases, because despite the increasing resistance, your current will decrease so much. So yeah, when someone's trying to ask you, how does your power change as you change the resistor? Just watch out, because in the most general terms, the answer is it depends. And for the specific situation that you might be given, you have to carefully think it through. Until you develop some level of intuition, it might even be good to just do a numerical calculation and get it that way. Otherwise, I would just keep this in mind. Remember that there are 1, 2, 3 different expressions for power, and which one is useful depends on the situation. And I think if you think through that, then it might help you avoid this trap that this trick question is trying to set you.